Hey guys, how's it going? Welcome to another episode of Ferris Makes Emulators. Another false start because I almost forgot to record. This is Bug Squashing Part 5. We're still looking into this bug here, which I thought I had fixed at one point, but it looks like I didn't fix it correctly. Because the fix I did ended up breaking Space Squash, which after some investigation, it looks like, looks like our fix was incorrect. So that's what we're going to be working on a little bit today. Specifically, I want to dig into this game again a little bit and just figure out like what it expects of the hardware when it disables the display and then unpacks the graphics. Currently, something goes wrong and it ends up firing an interrupt that ends up corrupting the graphics here while it's loading the graphics between screens, and so that's the bug. I had fixed this originally by disabling, triggering a certain interrupt when the display was disabled, but of course that made a Space Squash not boot, so that's where we're at now. That plus a lot of investigation and a couple hardware tests. So today I want to, dig into this game again and see what we can figure out. By the way, sorry, a couple people followed me while I was preparing, and I heard like the notification sound, but I didn't see who it was. So thanks for that. I'm sorry I didn't see. I can't thank you individually, so sorry about that. But yeah. By the way, hi to guys in the chat: Dark Second, Metal Void, Stano Colin, Tubez, is that he said? Duro2, and Ion Coates. How's it going, guys? Dan Collin says you reversed this decompressor, right? So yes, I did at one point. I think I still have those notes. I reverse engineered that, and so I think I remember where that routine is. So yeah, some breakpoints in there is going to be helpful. The decompressor itself was actually really, really basic. It's a really simple LZ77 kind of variant with like LZSS packing, but a little bit simpler than that. So it's a really, really simple decompressor. I can actually pull that up. But I don't think that that's going to be where the most relevant stuff is. Tobez, thanks for the follow. Appreciate it. Yeah, let me just pull this up because I have this in a gist. And I did make a Rust version, and I actually tested. So what I did with the Rust version when I was debugging this, this is when I figured out that like why this graphical corruption was happening, because this was actually the first bug that manifested that was kind of related to this whole thing. I did a blog post about it too on the Rush Boy site. I'll link that as well. And actually, that's probably the best place to find that gist as well, because it should be linked there. So this here is the blog post. Go ahead and link that here. Hey, Alkama. Yeah, so this is the post originally manifested as these graphical bugs, and as I was digging into why those graphical bugs happened, I noticed that there were some writes that it was doing to addresses that didn't make sense. And so I ended up looking into that a bit more and disassembling the code that was doing those weird reads and writes. And I found that it was a basic decompression routine, but somehow one of the registers was getting corrupted, and then it was reading and writing from places completely unrelated to where it was supposed to be reading and writing from. And as I looked into that more and then reverse engineered the whole format, what I basically did is I took the data that it was pointing to and then ran it through my own version, my Rust version of the decompiled code. And just I looked at the reads and writes that it was doing, and none of them were out of range. Like they were sort of normal. And that's when I realized, okay, so this routine probably is supposed to work like this, but then something is causing one of the registers to get corrupted. So of course, then I suspected that it was a CPU bug, but then as I sat there debugging it, I noticed that whenever the graphics were corrupted, it was an interrupt had also fired between when the function got called and then when it returned. And then as I just opened up the code for the interrupt and I looked at the registers that were preserved, and there were a couple that were missing. And it turns out that those are the ones in the graphics routine that were corrupted. So I want to... I think the only real clues in that routine that we're going to find is not actually in the reverse engineering or the reverse engineered code that I did. Okay, so here, by the way, this is the original pseudocode I made with just reverse engineering the routine, and then I did the Rust version after again so I could test the reads and writes. That's going to be in my gist somewhere. Let me look this up. So Design says, have you changed mic? I haven't, but let me actually check something because I noticed that someone was we seemed to be having issues with that on the stream that I was on last night. So let me look into that really quick. No, it looks like I'm using the right mic. Does it sound weird for anyone else? So Designs is not the same quality it used to be. Yeah, very strange because I'm definitely using the same setup. At least it seems like it on my end. But I know that I had issues with that yesterday. Hey, Snyder Delta and Dana Collins say it sounds good. Yeah, my settings look correct at the moment. But I did have issues with that last night on a different stream. But that was through Skype, so I probably had different settings there and messed that up. But I'm gonna go ahead and continue. Yeah, this was the Rust version, and I just hooked that up. Yeah, here's actually the whole thing. Here we go. Tomco sounds fine to me, but so does Design. Have you changed ears? Yeah, that might make sense. So what I did here is this is the ROM file, and then these are the two parameters to the function in the code. I can zoom in here a little bit. So this is where basically the data starts in ROM, and then this is where the data is being decompressed to. And then just had it run that. And all I was doing was printing out reads and writes, particularly reads. And all the reads looked very sane for what kind of decompressor this was. So for those of you guys that are unfamiliar with LZ77 base compression, it's basically you split up the stream, so you treat the data as a stream of bytes. It's a byte-wise compression algorithm. And what you do is you say you're going to output certain kinds of packets. And you either have literal packets, which is just a 1 bit, like a 0 bit, and then like a 1 bit marker that says like 0, and then the next 8 bits are going to be a literal byte, or you have back references. And how back references work is you identify them with a different bits. So for example, if you use 0 to identify a literal byte, you'll use 1 to identify a back reference. And you may have more complicated schemes as well, like you may extend those bit things for different kinds of back references, but raw LZ77 only has those 2 types, and this implementation also only has those 2 types. So if you have a back reference, you need to encode the address for where that back reference starts. And it's basically a pointer into the already decompressed part of the sequence. Or in the case of the compressor, the already compressed part of the sequence, but like the original data. And then also a length for how many bytes within that stream to copy. And it's pretty basic. In this case, I don't remember the exact format, but it's basically... it packs all those marker bits into bits, so like every 8 packets, it'll just have the bits in a single byte so that it can just read those all at once and then read those off. So that's what this packet flags thing here is. So it just reads that byte. It skips over a couple bytes. I guess here's a bytes left thing. I don't know why it's reading that there. But I guess the amount of bytes was packed within part of the data. That's fine. I think that's the uncompressed size. Then it reads the packet flags, and then for each one of those bits in the packet flags, it'll read the next byte. And if the flag was not 0, so if the bit was 1, then it's just a literal byte. So with this next byte that we read, it just outputs that directly. And then of course increments the output pointer. Otherwise it's a back reference. And so it'll take the data byte it read and then the byte after that as well. And with a couple shifts, we get the actual distance. So like the pointer, it's a relative offset from where we currently are decompressing, or sorry, currently decompressing to. And then it goes back behind that. And yeah, then it also reads a couple more bits from this original byte as the length. Looks like it can only handle sequences from 3 to 19 in this case. It's really common, by the way, to bias these lengths because like you would only use the back references to encode sequences that are going to be longer than it would have taken you to encode literal sequences, if that makes sense. So you're only going to use these for like runs of length 3 or greater, for example. So it's really common to then bias this length as well. You get a little bit more compression there because you can describe longer sequences by whatever this bias is. And then it just loops through that and then copies those with a couple weird details. But it's a really simple decompression routine. Yeah, and there's a couple more details that I don't particularly remember, but it's not very important. Anyway, at some point, I think it was the packet flags that was getting corrupted. So then it was just misinterpreting the rest of the data or something. I don't remember specifically, but we're gonna have to dig into some of that today. Like Jeff says, can the length extend forward like in gzip or deflate? I'm not sure in this case. I think it can. I think oh no, this was writing bytes for a special case of when it was behind the when the back reference actually pointed behind where the data started. It would output zeros or something. That was something else. So I think it can, just judging by this decompressor, but it's usually actually a detail of the compressor that determines whether or not it can do that. And I obviously have no idea. I could, I guess, look at the patterns, but again, this is not the problem. This decompressor works, and it's just very basic LZ77. And then I was able to, from reverse engineering that, figure out that, okay, this is what's happening, and this is what's going wrong, and this is why the graphics get corrupted. So somehow this game is suppressing this interrupt, or there's some conditional somewhere that's checking some registers that we may have implemented wrong, you know, something along those lines, that's causing it to corrupt these registers that the graphics decompression is using. So something like that. But yeah, I'm guessing this decompressor can handle that. I don't think it's relevant though. But I guess it's interesting for when talking about compressors. Hey Evil, how's it going? So yeah, always helps to have a little bit of compression knowledge when dealing with like anything. It was very nice to be able to recognize this while working on this. Yeah. But yeah, so I originally thought that the problem was that this interrupt was firing in the first place, and that may still be the case, that the interrupt is firing when it shouldn't, but I'm kind of suspecting that there may be some conditionals in the interrupt handler that we're not being able to support correctly due to something that we're not implementing. I'm not really sure. Need to disassemble some more stuff around there as well, so we're gonna have to just sit down and make a lot of notes today, I think. But hopefully we'll be able to fix this and then have this and Space Squash working, and it'll be a lot of work to get yet another game in the playable list, but it'll also be more correct emulation. It might fix some other things, but we'll see about that. So yeah, I guess we need to start digging in. Actually, I'm gonna go ahead and look at my hard drive again. I found this last time, but I forgot where it was. I'm just gonna go ahead and find my notes from the last time I looked into this. And the reason why I want to do that is because it should have some addresses for where these routines were. And also it should have the code for that. So I just want to look in there. I think it's this one. Yeah, here we go. So these were the notes that I took when originally disassembling the routine. It's not terrible. So what this was, I think this is some of the compressed data. In fact, I think this address matches the one in my gist up here. 9FB4C, yeah, that's this. So at this address, we're looking at this, and this is the compressed data. And the first thing, of course, you notice is that these 2 bytes are skipped. If we look at this piece of code, I'll just skip the first 2 bytes, and I think that disassembly, I don't think I have the disassembly in this part, because what I did is I took a dump of the routine itself, which is this range here, and I basically just pasted it into here, and then little by little, I replaced little bits of the code. Like, oh, here's a loop, so we're gonna say, okay, variable A, we just called it whatever. And then, like, slowly kind of took out the structure here. And the first thing I remember it doing is just incrementing this address, so that's all it really did. It also takes in the source and destination, which are just pointers here. Yeah, do those. Here's some notes I had about the locals, which registers they were in. And actually, this I think was the one that was getting corrupted now that I remember, because I'm pretty sure it was R12, but I could have been more of these. But length of the uncompressed data for this run. So I think that's here where it gets the back reference, and this length gets corrupted, I think was the issue. But yeah, I'll have to get another dump of this routine. So we can start with that, actually. So I'm just going to break into the debugger here. And I'm going to go ahead and mute my system audio, by the way. In fact, I'm also going to put on some music while I do this, because that's going to help me do this properly. Glad to hear the audio's fixed. Let me pull up some music for me. And actually, really quick, just had to mute my system audio here to make sure that I don't end up playing something copywritten. Okay. So I'm just going to go to this address, and then, how long was this? Not that long, 35C to 496. Let's do that twice, then we have everything. And 496 is up here, right after this jump here, which is going to be our ret. Let's go ahead and look at this. Copy this out here. And already you can see a couple things. Where's my syntax? Where'd my assembly go? I could do kick assembler. That didn't really help. Anyway, here, for example, this is add 2 to R6. This right here was the incrementing that address. R3, by the way, is the stack pointer, so that's what that's adjusting. R6, I guess, was this thing here, this source. It just increments this. I'm going to go ahead and add R6 here. I'm pretty sure this was R7, and I think actually at the call site there was... So these registers are commonly used for arguments with this compiler. And then, yeah, I think R7 was our destination pointer, which makes sense here because we do a store and then increment the address. So I'm pretty sure that's correct. And I think there was a third argument as well that was like always 0, and I don't think it was ever used. It was that would have been R8. Yeah, we can't even find that, so that makes sense. So that's all we need there. What I'm more interested, though, actually, is finding a case where while this routine is running, we get an interrupt. So what I'm going to do is I want to set a breakpoint at the beginning of this, and I want to set a breakpoint at the end of this. But I'm going to disable those. And how do I want to do this? Actually, I think it's fine if I just set those breakpoints. And then I want to have the game go into a screen transition and trigger one of these. Now, when that triggers, I want to set a breakpoint in the video hardware interrupt. And I want to basically get a case where, yeah, the interrupt fires while this is going. I think that'll be okay. Then I want to go through that interrupt code a little bit and just kind of look at what's going on in there, see if we can find anything obvious that would affect the code here, in particular the registers that we know are getting clobbered. And yeah, start there. And then the other thing I want to do is I want to look for places that call this. I think last time I did that, I just would set a breakpoint in here, and then a few times that it was called, I just jumped to the return instruction and then followed that and just like disassembled a little bit around there and kind of got a better picture of what was going on. Also, I want to have it print out some when it's going to read and write to some of the video registers, so we can kind of keep an eye on that. And hopefully just by digging around here a lot and not really trying to see too many patterns, but just trying to gather all the data we can, hopefully something will emerge. I think that'll work out. Evil says, what is VIP mem? So VIP, that's the video hardware. I guess you're asking about this into decompression into VIP mem. Yes, VIP is the video hardware. This should really just say like VRAM, I guess, but it's not always VRAM. It's sometimes to go into the character RAM. So I remember this routine being used for a few different things. They seem to compress all of their pixel data and their map data using this scheme. So, by the way, if you're not familiar with the LZ77 compression scheme, if you've never written one of those, I highly recommend you do so. They're actually surprisingly effective for how simple they are. And if you are ever looking into getting into any kind of compression, I would definitely recommend starting there, just because it's so simple and surprisingly effective. Like they're not great, but it's like works pretty well in a lot of cases. And if you pack with doing the like packet marker bits, if you pack those into a byte like this one does, then at most you have like a 12.5% expansion in the very worst case, which you almost never get on actual data. So it's pretty cool. eHiggs Switch is 77 or 78 easier to implement in your opinion? If I remember correctly, the differences are actually very small. I think 88 would allow it to go past the pointer, and maybe there are a couple other differences. But the important part really is just understanding that back reference concept. Like sometimes you have literal bytes and sometimes you have back references, and just kind of playing with that idea. I think both of those are just kind of variations on that concept. So what I mean to say is the LZ77 family. Yeah. But yeah, I would recommend looking into those at some point if you're interested in compression. Good place to start. I think they're a lot easier to understand than like LZW, which builds an explicit dictionary, whereas these sort of use the parts of the stream that have already been compressed or decompressed, depending on which perspective you are, the encoder or the decoder. And it kind of builds an implicit dictionary in there with the back references. eHiggs Twitch says, Mr. Wiki says they're equivalent, but 78 can decompress ranges in the middle of bytes. Yeah. Sounds about right, I guess. Evil says, bring back Zoo. Man, that's been a long time since I heard of that. Old file format. Yeah, it's based on LZW. That's funny. I think the very first compressor thing I ever wrote was LZW, and it was based off of some old Dr. Dobbs article from the late 80s. And I would have written that in Blitz Basic in 2005. And it was really bad how I did it too. But it did compress the data that I was working on at the time. I really like data compression. Anyway, time to look into some of this stuff. Yeah, so what I'm going to do is set a breakpoint here. And we shouldn't actually hit this. If we go back into the game here. Did we hit that? I did not expect to hit this. Here we go. Okay, yeah, I guess we were changing screens. So now we'll hit this when we go into the next screen, and that's what we expect. So if I go into here, then we'll hit it. And we'll hit it a few times because it's going to decompress a few different chunks of graphics. And now here we have the broken graphics. So that's exactly what we expect. If I hit B again, then we go into this routine again. And I'll just hit continue a couple times. Oops. And then we're back to the screen with corrupted graphics. So in at least one of those times that those graphics are running, this interrupt fires and wreaks havoc. So now what we want to do is I want to trigger this again. And now that it's happening in this routine here, I want to add another breakpoint to the end of this. Now, the end of this was 9.6, but that's actually not the end we're going to find because we're actually not going to hit the code that's there. We actually want to set a breakpoint here on the return instruction. So I'm just going to go ahead and add a breakpoint there. And at the same time, I'm going to add a breakpoint to the video hardware interrupt. That's going to be FE40. And if I continue there, we're either going to hit the return address, which is what that was. I'm going to skip over that. We're back into the compression routine. And now we just got a video hardware interrupt in the middle of the compression routine. That's what we wanted. So if I disassemble this is right at the end of memory. So this is the kind of stuff we need to do today, is just collect a lot of this stuff. Like, where are these interrupts located? It looks like this one's going to be in FFF800AA. I'm going to go ahead and just step into that a couple times. Yeah, it stores that into R11 and then jumps there. Yep, so here's our routine here. I'm just going to copy this address out because we need as much help as we can get just finding stuff here. This, I actually want to split this up into a couple files here. A VIP, again, is the video hardware. So I'm just going to have this. I'm going to go ahead and save this, by the way. And yes, I have some funny stuff on my desktop here, but no worries. What did I call this? Yeah, I'll save this one too. Why not? Yes, this is our VIP interrupt. And then here, what do we have? So what it's doing right here, by the way, I'm actually going to copy all this out here. 0016 is actually where that ends. Whoops. Oh, crap. Did not mean to close that. So now I have to settle that up again, but that's fine. I hit Control-C, which I meant to copy, but that happens. Yes, this is the VIP interrupt, and all it's doing here is pushes a bunch of these registers onto the stack. You'll notice that R11, R12, R13 are not here, and that's already enough to mess up this code. R14's not here. A lot of them are not here. So it only preserves some of these registers, then jumps to this routine, and then will preserve the registers and return from the interrupt. So that's all it's doing. I need to go ahead and set that up again. There's a reason I didn't do this on stream initially, and that was just because this is kind of annoying to set everything up, but that's fine. We want to trigger, whoops. Why did that happen there? Did I add the wrong handler address? Oh yeah, 9.6 is not what we wanted. We wanted 9.4. Okay, there we go. That makes more sense. And then we'll make this fire, and then we're going to go ahead and add this again. Okay, made it through once, and there we go. Bang. So it breaks into there pretty consistently, and that's fairly interesting. The next thing we're going to do, so it jumps to this address. And actually, here's what I'm going to do. I'm going to remove this one and add a breakpoint here in the actual address, and it's going to get there. Just going to disassemble some of that. By the way, again, I rave about it all the time, but if you're doing an emulator like this, do a debugger. It really helps. Okay. Now, there's generally going to be a lot of stuff in here, and I don't think we're going to need to understand the vast majority of what's actually going on here in this interrupt. What I'm doing, first of all, is I'm looking for a jump back to the link register, because I want to just copy the code for the whole thing first. And this goes to B8, just back here, so this is some loop. Back there, C6. So I'm just kind of scanning this. It should just be going forward until we see the ret, but I want to watch some of these addresses as well. This one looks like it, but it's not, because this is R30, not R31, which is going to be our link register. Here's one, but it's probably going to be the first one that we see here. It might be a couple more, so I might grab more code than we actually need here. But I'm guessing, especially because this seems to load R31 from the stack, and then adjust the stack again, it's probably this one. And these others are likely other subroutines. Yeah, I'm guessing it's this. So we're going to go with this first. We can always just disassemble this again if we miss something. That should be fine. Hey, local hoster. Like, the only thing that would actually be relevant here is stuff where it destroys the values of these registers. Realistically. Stuff like R11, R12. These things seem to be used for just locals. And in particular, those are the registers that get clobbered in our decompression routine that causes the errors. And one of the things I noticed just by highlighting these registers here is I noticed that before that, it looks like there's actually a branch here that jumps over this jump to 590. Now, where is that 590? That's out here. And the reason why that may be interesting is it looks like there's a couple conditionals that just jump over a bunch of stuff here before the end of the routine. And I think last time I looked at this, I assumed just because I knew it touched those registers that the whole interrupt wasn't supposed to fire, but I think we might have to dig in a little bit deeper to see what are the conditions under which those actually are touched. I think that's what we'll have to do. I'm guessing if I step through this, in fact, I'm actually going to hit add a breakpoint here just to make sure that we exit the routine through that. So if I do this and then continue, we should go straight to there, and we do. So that's a good sign. and then the next breakpoint we hit is going to be the end of the decompression routine. So that makes perfect sense. Now it still might be possible that we would exit this routine through those other jump back through the link registers, but I'm gonna say that that's unlikely. In fact, one of the dead giveaways is that this here adjusts R3 by this amount, and I'm guessing if we looked at the top of the routine, we would see the opposite of that. So these definitely match up here. This prologue here, which reserves some stack space, matches up perfectly with this adjustment here before it returns. So we can go ahead and isolate some of that. In fact, some of this might be the epilogue as well, but I'll just mark this so far. Mark the prologue up here. And I think, actually, we'll put all of these pushes here just because at least it's symmetric that way. A lot of this stuff just gets super tedious, just digging through a lot of this stuff, and you just gotta sit and chug, and eventually the patterns will come. So right off the bat, by the way, this is touching VIP registers. And I'm guessing that some of these branches we saw that was going to jump over a lot of this stuff is going to be branching on those register values. And if one of those, if we can sort of find a conditional that will jump over basically anything that affects these registers, that's based on some register, it might be that we have that register implemented incorrectly. That's what I'm thinking right now, at least. In particular, this jump to B8 is really interesting to me. Just because it jumps over so much stuff. So one of the things I'm actually gonna do, I'm actually gonna mark this B8 here. I call this label A. The only place where we didn't want to do that is here. That's why I copied that. Now I'm calling this like label A just because we kind of just have to enumerate some kind of label and we don't actually know what this is. But in particular, I just want to see like 60A here, and then it goes really far out here. I just kind of want to know what is it trying to do here. I'm going to call this one label B because it looks like these are sort of the top level conditionals here. And we can't really know what they do yet, but figure that out. So the interesting things here are that if it, where's this here? Yeah, if at this point, if it jumps to label A, and then subsequently jumps to label B, it shouldn't touch its case. It touches R10, R0, and R1, or 10 and R1, and then some other things that it preserves. Now, R10 and R1 are both registers that it preserves, so I don't have to worry about those. And I'm guessing that before this, it only touches R10 and R1 as well. So I'm picking these out because if it just does that, if these conditionals work out so that it just jumps over all this other stuff, then the registers that are getting clobbered that break the routine never get touched. So there's some low-hanging fruit, maybe. Yeah. We'll start there. This is a really common pattern, by the way, that it loads this value in particular with move high into one of the registers and then does addressing by that. What it's doing here is this offset, if I remember correctly, was RAM, I think. 500 hex. Let me look at my memory map again. Oops, actually my mem map. Through a quick question: what's the live coding software you usually use when making demos? It looks awesome, and sorry for interrupting. Oh, no worries. It's called Demotivation. It's my own custom demo tool. I have a couple in the earlier Ferris Makes Demos videos. I do a couple streams where I go over that tool in particular and the different pieces of that. I think was it the first one I did goes over that? No, the first one goes over Wavesaber. I don't remember. It's in the title. But look for Demotivation, because that's what it's called. Which is a play on... It's a word that starts with demo, and motivation is actually what I always find is the hardest thing to find when starting a demo sometimes. So it's just kind of funny. Yeah, no worries. So this is work RAM. This is the RAM. I initially thought it would be either the system registers or the VIP registers, but it's RAM. So we may have to start trying to look at the values that it actually looks up from RAM. These offsets, by the way, are the offsets it's reading directly from there. Just going to look at this. So the thing that it checks in particular is it loads... Yeah, it compares R10 to 0. R10 comes from this. Daniel Collins says, I think the Fairlight editor is called Demolition. Yeah, that's totally where I got the idea to put demo in the name. Because Demolition I thought was a really cool demo tool name, and I thought I could kind of make a funny version of that. And that's totally where Demotivation comes from. I like to inject little lame humor jokes in a lot of the things that I build for myself. And just a lot of the things I do generally, because I find simple humor amusing. And it's important to keep amused when working on stuff. Like my demo tool is Demotivation, and our group Slack channel is Conspira Sucks. Just goofy stuff. I like that. Let's see. So it looks like it just... We see this offset 24 here, and this is not in hex. This is actually 24. There's gonna be 1 8 hex. From this value. So I'm actually going to dump RAM here. I'll come in Wavesaber, exactly. Wavesaber is also one of those names where it's just like, I intentionally made it sound over the top in 80s because I thought that would be cool. Through says, I'm currently learning C++, really want to work towards graphics programming and hopefully one day making my own demo. Any tips for a beginner? What sort of things will I need to learn? You're going to need to learn some kind of graphics API right off the bat. Or you're going to have to use an engine, for example. Like if you're going to do C++, one of the things you might want to look into, especially if you're just like starting out, is actually like Unreal Engine. I would highly recommend looking into a bit of that. First of all, because you'll see kind of how these bigger engines are structured. And you'll also be able to, like, I think, get to something demo-ish a lot quicker. Like if you learn C++ and you get kind of experience with that kind of engine, then I think you'll get a lot of ideas that if you wanted to do your own engine instead, you could kind of pull ideas from that, but also you could be like learn really relevant skills that will take you beyond just doing demos with C++. Like if you ever wanted to go into games, then that would be relevant experience. And then you would kind of already be at that intersection of C++ and graphics. So I think that would really probably be a good idea. If you want to do it without any of those kind of frameworks or anything, you just want to do it bare metal, then learn at least some kind of graphics API. Metalvoid says read a lot of code. I totally agree. Daniel Collins says middle ground for engine is BGFX. I've never used BGFX myself, but I would definitely take Daniel Collins' recommendation on that one. Because one of the things that happens, especially when people want to get started in the demo scene, is like suddenly you need to import assets, you need to play sound, you need to do all these other things, and it's much better to like pick up a library to do those things at first, because it's a lot more motivating to just like start building stuff, I think. And then of course I love digging deeper into the tech and making all those tools eventually, but got to start somewhere. And I used to recommend stuff like learning OpenGL or DirectX directly, but it's kind of hard to find like really good tutorials for doing that at this point, I think. At least, I mean, I haven't looked in a long time, but the tutorials that I know of are definitely outdated. And I kind of have the sense that a lot of those are still the same way. Although I think like learnopengl.com was really good. I think that's pretty good these days. But you kind of have to decide if you're going to learn DirectX or OpenGL. And at this point, they're both fairly modern. Of course, DirectX is always a bit of a better API, but depends on a lot of things. Anyway, there's just some ideas. Drew2 also recommends open frameworks. I stand by that as well. Open frameworks and Cinder are both good things to learn. Yeah, no worries. I want to see more demos. I want to see more people making demos, so always happy to contribute to that. Oh, sorry, my back just got really itchy. Alcanos says join the demo scene. And bring friends. Yes, do that. Do both of those things. In either order. Okay. Where was I? I totally lost my train of thought. Oh yeah, I was gonna dump memory. Whoops, that's not what I wanted to do. Was it M? Yeah, there we go. M for mem. I'll comment. Damn, we did it again. We derailed the show. Honestly, I do this so I can get derailed a bit. Do not worry about that. I don't worry about that anymore. Nah, I don't need to apologize. Ah, sorry, Metal Voids. I need to add you to my whitelist. Links are still disabled, especially while I'm still doing emulator stuff. Not going to budge on that, but I'm happy to add people to the whitelist eventually. So let me fix that really quick. Sorry about that. Also, you can whisper me the link if you want to. That's generally considered quite okay. I generally add most people that I recognize. Like if you've been in the chat a few times, I have no problem adding you to the list. Just don't want something that'll get me flagged for copyright to show up or something. Now you should be able to post the link, Metal Void. Sorry about that. So this is just an example mem dump of the work RAM here. Most of it's down here is not being touched. I think a lot of the globals actually go to the top part of the memory of the work memory, if I remember correctly. So not entirely sure what this is going to be. But it does some stuff with this offset and this. Okay, this is R10. So it loads a pointer from here. Excuse me. It loads this here. F800. Or sorry, no, it loads that whole word, so it actually loads this. Which is little endian, so 0005 F800. It's going to be right after this, actually. Or no. It's going to be, yeah, pretty far away from there. It loads a pointer. What does it do with that? Loads it into this value and then stores into that value plus 4. Not entirely sure what this is, but this compare that we're actually looking at doesn't seem to be related. That's why I went through that. I wanted to see if it was related to this compare here. It doesn't seem to be. So it loads 500 plus 24, which in hex is 18. So that's going to be here. And it loads that as a half word. So it's these values here, 2. Is that correct, or did I go one more? 0, I think. Yeah. So it loads that half word there into R10 and then compares it to 0. And if it is 0, it goes into this routine where then it goes and does stuff. So if it's not 0, that's when we're going to skip everything. Seems to be the case. So this could be anything. Could be some kind of mode. Could be anything. Just going to make sure that was a LDH. Yeah, I think it was. Yeah, I still use cppreference.com all the time, by the way. That never gets old. Or, well, anything gets old, but you know what I mean. Tricks that against 0. Then it loads. By the way, you'll notice a lot of this is redundant. Like it always loads this 500 into this. The compilers they're using for this stuff does a really bad job at optimization. And I was talking to someone about that who was a little more knowledgeable about this kind of stuff around this era, and he was basically just saying like, yeah, I mean, it kept your compile times down and the code was still small enough. And the thing was that if you ever had to actually optimize this even more, like people just kind of knew how to write assembler, how to do inline assembler and write these sort of inner loops that way, and that makes a lot of sense to me. So you'll see a lot of this redundancy is the point. The compilers just aren't going to take care of a lot of that at this time. So it does that, and then it looks at this 1-4 here. It's also a half word there, and then compares that because it'll also jump over that in that case. And that's this value. Where it's not 0. Some other mode or something, and then it will jump over all of this stuff then. And then it takes whatever it loaded from R20 into there, which is interesting. And then checks a certain bit in there. Where did R20 come from? That was loaded up here. Oh yeah, from that pointer. We'd have to see what that is. I'm actually kind of curious what's in there. Wait a minute. Is that right? I think it is, and at least we have some kind of pointer, it looks like. But it's not where I would have expected this to look. Dark Second said, wouldn't it be 500000 F8? I don't think so, because it reads it as a word. Where a word is 32 bits here. So I agree that it's weird. Like, that's what I would have expected it to be. Or 0500 F800. But as I'm looking at how this would be interpreted, I don't think that's the case. Or yeah, no, because even if it read it as two half words, those would be little endian and it still works out. So again, this is not where I would have expected that to be. But I think, let me double check where this is, because I think this is in VRAM, which is kind of weird if it's storing state there, but what's our memory map say that's down there? Oh, wait a minute. No. 5F8, this is, why do I recognize this value? It's been too long since I looked at this. I am fairly certain. What was this address here? Here we go. That's the interrupt pending register. Of course. That makes sense. That's how I recognize that address. No, then it makes perfect sense. So what it was doing here then, let me go ahead and mark some of these things in our notes here. So it looked like this is a pointer here. And it's probably going to stay the same here. So R10 is equal to so this basically tells the program which interrupt actually fired, and let's do here. Right, and then here moves into R20, and then it stores the half word 4 bytes over that, which, if I remember correctly, all of the memory addresses in the VIP are 4 bytes apart. Oh, they're actually not, because the enable reg is here. No, this makes sense. So it takes whatever value it read from the pending register and it writes to the clear register, which will clear those bits. So that actually makes sense. So R20, by the way. So that actually makes a lot of sense. So that's what it's doing. Okay. I don't know why that felt that confusing, but that's very simple. At that point, then it starts digging into work RAM. That makes sense. I'm just going to add this little note here as well. Kind of strange that they did it that way, but see a lot of strange things when you start assembling these games. And it generally looks like R10 is just some temp register that it's using a lot. And that's probably fine. But yeah, so it would get this value. And all that's doing is clearing that register, I think. Interestingly enough, I would have expected it to at least use, like, check which ones these are. Okay, actually, that would make sense if that's all it does, because that's probably why I concluded before that the fact that the interrupt fired at all was the problem. But maybe it's not, because it does do some conditionals that check on certain states in here. And we don't know what those are yet, but just got to keep digging. I tend to write little notes like this. So for example, this was something, I think 24. Gonna be 18 hex, which should be here. We don't know what that is. Hey, Love Like Semtex. R10 is going to be whatever the value was at. Oops, that's there. And that's a half word, so it's only those 2 bytes. Evil Access, search for Nihi Game Dev and click the first link. I'm sorry, but please don't do that. Those are not modern GL, and I don't think you should spend your time learning that. Specifically, avoid those would be my advice. Sorry, Evil, but I just really don't want new people learning from those materials. Some years ago, I would have totally agreed, but not anymore. I'm just gonna add a lot of notes here. And it looks like, yeah, 14 from here, which is going to be these ones. So I'm going to add a similar note here. And of course we see 1 here. Notice that I'm writing this in terms of the actual value, even though here it's stored little endian. Sorry, I just Googled to make sure it was little endian, like I remember correctly, but it must be because otherwise this would have been weird. Oh, sorry. I wanted to write mode here. That's what I want. And then I'll do the same here. 14. We've seen 2 there, but it only compares it to 0, which is somewhat interesting. But also interesting here is the fact that in this configuration of values, we had 0 here, which brought us here, and then here it would load this value, which is 2. Compares it to 0. And if it's equal to 0, it jumps here. Otherwise, we jump to this label A. So let's look at what... So it does actually jump over all this. Okay, so it looks like it actually keeps R20, in this case at least. So R20 will have kept the same value in this case. And in fact, I bet if we see some code up here, yeah, this actually just jumps over this stuff anyway. Or no, that's actually after it was writing this. So this would have changed it. I'm not really sure why it would do that, but I'm not entirely certain. Anyway, what it does is it ANDs it by this mask, and I'm pretty sure this mask was our start of frame interrupt, which is the one that is firing here. Now, what would be nice about that is we might actually be able to figure out where it's touching those registers in a very small amount of code, and that would be nice. But you never know. Let me double check that again. Here, that is the proper mask. Yeah, that should be. And if that's not 0, we're going to jump here. So this actually specifically checks for this particular interrupt, because it masks out that specific bit. In fact, actually, we can sit here and do this even. Do this. Something like that, to kind of just lift some structure here. So if this, basically this clobbers like any of the registers that we expect it to touch, then, which it looks like it does already here. Did I write down which one R11 is using in this routine? I don't think I did, but I'm pretty sure R11 is just generally used a bunch in this routine, just as a like temp variable. So it'd make a lot of sense if that messed something up. Okay. Anyway, it loads this back into here, and then we're loading from 16 again, which, if I remember correctly, is this again. Yeah, here. So we're going to copy some of these here. I think that's movie A, like that. That's what's going on there. And then it jumps to this routine. We don't know what that is yet. What is this? 26? Is that this? We don't know what it does with this yet. Wait, sorry, that said 26. This would be 22. 26 is over here. This is the annoying part about doing little notes like this, is that we gotta sometimes do this stuff, but that's okay. Ah. Oh, by the way, someone earlier asked, Dark Second asked if I could set watches. I can actually do that and should watch some of these variables, see what they change. But I'm gonna finish these notes first, I think. Wow, I'm so bad at finding some of these symbols sometimes. Okay. Now this actually wouldn't run in this case with the value here. Let me double check that that was the right interpretation of that. Yeah, that should be. Again, we're a little endian. And that value there does not have the 1-bit set. Not sure what this does, but. Guess we can skip this though. This is actually else. Because this will jump here, and then this will do this. Otherwise, this jumps over this. So this else construct here. And it stores whatever this variable is. Stores 0 into whatever this is. Just do this conversion really quick. Eight, 6, 7, 8. 2 on E6. Hey, Studio C. This is an increment here. All this here. Whoops. Sometimes when I figure this out, I like to just get rid of this. No, this is not. Oh, yeah, it is. Yeah, because we. All this is. Yeah, that makes sense. So that enter 10, increments that, and then stores it back. We don't need this either because we figured this out. And this whole thing is also this. So we can comment this as well. Yeah, same bug. Yep. So I'm actually going to remove this. So get rid of this to reduce visual noise. Don't know what this is. Actually, we can do this to check that really quick. 8678. Is used here. A couple other places, but we'll see. A couple other things. I actually want to do this here. See if we can fill in some other values seen for these here. At least in the context of the graphics being corrupted. Probably a good idea just to get a little bit more overview there. Yeah. By the way, one thing I want to do actually while I'm doing this, I'm going to add a couple labels here. Just so we can see that as in the little thing here instead of just addresses. See if I remember my syntax. I think it was the address and then the name of the label. Did not like the syntax there. Can't remember which was the start and end of this routine. There we go. This is actually the decomp end, I think. Okay, we'll do this. Decomp start is FF8135C. 494. Yeah. Now we can see we get these little labels here. That's why that's useful. Yeah, so that's the end of the decompression routine there that we hit. And that's interesting. We got another interrupt. Interrupt fired twice there, actually. That's interesting. Just gonna fire this up again to see if we see any new values here. New one there. So actually, I want to go ahead and see what else we saw that used this. Where else would I put that? This would have been 14. Okay. I guess I had this note wrong. Anything else that's different here? It's the same. That's the same. That's the same. I got the interrupt handler again. Oops. Same stuff here. Although this might actually be particularly interesting because if it's 0, then we're actually executing the code in here. So there may be some fairly interesting stuff there. So the chat is pretty silent right now. I'm surprised at how much this is firing here. I wouldn't have expected to see this popping off so much here. This seems strange, actually. Why are we hitting this so much? Oh yeah, because we're actually in the routine. Okay, never mind. Seriously, since people need the golf tune going on, yeah. This is actually interesting though, because I think this this state here, this might actually be whether or not we're in a screen. I totally forgot to watch this while stepping through this. We actually need to remove the breakpoint in the handler. What are my labels? We're gonna remove the breakpoint from the interrupt handler. Here we add some more notes to this. This could actually be really interesting. Because if this is a state that determines whether or not we're between screens, then that's probably very relevant. Back to 0 here again. I'm just going to pause a random frame in here as well. Oops. And look at this value. Looks like we're still 0 there. Continue for a few frames. It looks like we're still 2 here. This is still 0. Which is basically what we expected. The other thing I'm going to do, I'm actually going to continue and see if I do this and it breaks here. Here, this is set to 1 again. And in fact, I'm going to add a watch there now. 000E is the address. We're going to hit some decompression start and decompression end. And you'll notice it just broke somewhere that we haven't seen before. This usually happens after the watch points. Currently, so we do actually have a branch with traces that I still need to get into the habit of using. But basically, this will break after the instruction that hit the watch point rather than before, which is not the best experience ever, but it's really not that bad. 02C2. So all I tried to do there is just bump up 4 bytes before the instruction that we saw there, and it looked like it loaded this value into R10. So it's probably reading the value there. And that actually we should have expected. Not going to worry too much about that. Here we hit a different one. Whoops. I did not mean to disassemble that much. FF9. 0F80. Okay, so here it's stored R6. If we look at the registers, we're going to see R6 probably has a 0 in it. And it stored that into 14, where R1 is probably going to be our RAM here. So it looks like here is where it actually stored where that was going to be. So that's fairly interesting. I want to actually take this, and we're going to add a label to that. Set mode 0, which is just going to be helpful for now. And I'm going to continue on this. So 2C6 is where it checks the mode. Particularly interesting, 5B4. Whoops. You know what I'm actually going to do? It keeps... Oh yeah, I know what's going on here. It's got to be just reading that value again, I'm sure. Yeah, it probably reads it in R10. Yeah, same thing here. And then it's sitting there. It's sitting there in a loop looking at that. So I'm going to remove that watch, actually, for now. Continue, and then we're up here. The last thing I want to do, though, is I want to see if we can get so that we can see when that value changes. because it looks like we found where it sets it to 0, and I want to do some disassembly there. But I also want to see where it sets it to 1. And unfortunately, I don't have watches that actually look for conditionals there. I could hack it in the emulator, though. See if it sets it to specific values, but we may not need that. But I'm guessing it's still going to check that every frame, and we don't want that. If I just hit B and then F12 really quick, that should actually help. Now I'm guessing at least it'll still probably check it, like, hopefully not in a loop, but maybe like every frame. But we should be able to, yeah, hopefully see it there. It's the same thing we saw before. Okay, maybe this does check in a loop. Yeah, unfortunately, this actually does sit there and check in the loop. That's a bit unfortunate. But one thing that we can do... Oh, yeah, this just sits there while it's 0, actually. I may have to hack the emulator a bit to break when it sees that one value going there. But I'm guessing, so we saw it was, so if I look at it now, though, we see that's 0, and I still think that's like 0 in-game and then 1 when it's loading screens or something. I wonder, actually, if that's consistent with when it's loading other screens, or if it's like specific to that one. Oops. So I'm just going to let this, see if I can catch it switching screens again. Actually, I should be able to, because it'll just hit the decompression stuff again. But this is actually like exactly what I expected, though, is that there's some kind of mode here that might run this code conditionally. So there may be something good here. Yes, now we're switching to some kind of screen. If I go here and check the memory, now it's 1 again, which is what we expected. If I wait for the decompression stuff to end, we'll hit the decompression stuff a bunch of times, loading a lot of new graphics data. Quite a bit. It's still running even. That's somewhat interesting. But maybe not that surprising. Maybe it was loading some stuff here. If I break here, though. Well, what? Break. Why is this running? I wonder if I had some input stuff buffered. Anyway, if I go to here, now it's 0 again. So it seems like this holds, which is fairly interesting. So this might actually be like an is loading flag, which could be really nice if that's what it is. And then this can make sense here. So this is some other state, and then it would check if it's loading here. And if it is loading, it doesn't, then we're basically going to be done. Although it already clobbers R11 here, which could cause problems for us. Oh wait, did I read that wrong? No, because this jumps to label A, yeah. And that's down here. Then this is where it would matter in particular. And again, this checks that specific bit. If that specific bit is the one that went off, then it clobbers R11. we don't want it to clobber R11. That's quite bad. Not preserved there, and again, it's not preserved by this bit here. Oh, wait a minute. Wait a minute. Wait a minute. Wait a minute. This might actually be totally fine. Because we have... It's loading R11 here. Did it use R11 to jump into this? It did, didn't it? Okay, so actually R11 is preserved. So that's good. So we're going to remove our notes about R11 being clobbered, as we don't care about that. So throughout this, let's say that this was 1. R11 is completely safe here. Or, well, yeah, we don't care about R11, but like R12 and stuff is completely safe here throughout this entire routine. So depending on what this does, it's got to be something in here then that's messing that up, I would imagine. Although... it was somewhat interesting. Runs the decompression routine a bunch. And then the screen starts showing. It was somewhat interesting that when it went into the demo mode, it kept doing the decompression routine. However, the decompression could have been anything. Could have been graphics, could have been whatever, because the routine takes the source and destination buffers as like any value. I'm just going to wait for this to go in the demo mode again. Actually, I'm going to force it to go into this other mode first, because I just want to see. Like, what I'm checking is that it seemed a bit strange that when it came back into that other screen, that it was still running the decompression routine a couple times. In this case, it didn't look like that was the case. So I'm going to go ahead and go back. We seem to be okay there. By the way, really quick here, I do want to copy these out just to have these in the notes. It's so funny how that doesn't affect any of the game logic. Just bugs out. I'm starting to get hungry. I had dinner really early in the day today, which is dumb. Yeah, because it ran this routine a bunch of times. And I just want to look at this value again. It's still 1 here. And here, the game's starting up again. And our value is 0. However, one of the things we can do, we are at decompressor start, so we can look at the registers. And R6 was our source, and R7 was our destination. So this is a bit odd, because it's still... the screen's fading in at this point. But it still looks like it's decompressing into video memory. So I would have expected that this is probably going to clobber some graphics as it's fading in here, just because if this was what was protecting it, then that doesn't seem to be the case anymore as it fades into this screen. But it's clearly okay, or probably okay, because the graphics were still corrupted on transitions to and from other screens. So it's probably not that relevant that still happens while this screen's fading in. Might be, but probably nothing to worry about. I'm just waiting for to switch back to the other screen. Oh, actually, I could probably hit a button. It'll do that. Sometimes it works out, but I think that's more coincidence than anything. Okay, so it looked like we found a state that at least seems to determine whether or not a screen is supposed to be being displayed or not. That seems to be fairly relevant, because at least there's a bunch of stuff in this interrupt that only runs when that happens. And that honestly could just be like game logic or something. In fact, that's probably what that is. Regardless, it always seems to run this code whenever it's the interrupt pending reg that fired this. And then we jump into this routine. So we have to dig into here, see what this is doing. And if it touches any of the registers in question, it probably does. In fact, I'm actually going to add a breakpoint to that routine. There's 4C. So there it was. That's the routine that it calls. Reserve some stack space. Pushes our link register on the stack. This is probably loading a global. I think R4 is usually where the globals end, and then it's usually indexed this way. But avoid says this is like black magic for me. It's one of those things that you just like I even notice it when I put this down and pick it up after a while. It takes me a minute to kind of get in the zone and start being able to read this more naturally, but then it's like that scene in The Matrix where he doesn't even see the code. Just blonde redhead. I'm going to look at the registers a bit here that it's messing with, and I'm also going to look for it to jump back through the link register, because those are going to be the more useful piece of information. Also, if we see any other jump and link instructions. Those may be relevant. Like this one, some subroutine. I'm way faster at reading x86 than I am this architecture, but that comes down to experience. That's just where I have more experience than reading this one. R15, R13, so there's a relevant register there. R12 here. So whatever this routine is, it's clobbering some stuff, but hopefully that's behind some conditionals. that's checking values we can fix. It's a bigger routine than I would have expected. Darksican says x86 also depends on the tools and compiler. IDA is still king. Yeah, I'm a bit old school. I use Ollie DBG still, and that's just one of those tools that I'm so used to, and I just swear by at this point. But IDA's definitely better. But I don't have an IDA license. It's a bit pricey. I played around a bit with Radar, but I'm not taking apart enough stuff where that's really particularly more useful than a dedicated debugger that also has those features, which is usually what I need. I'm usually writing x86 rather than reading too much of it. And even then, it's not the most often I'm doing either. Yeah, Radar definitely is a big learning curve. One of those tools I feel like I could get really good at using, but I'm just not doing that stuff enough to really have it make sense to practice that so much. CC says Win32 DASM. But avoids now. Does anyone have an idea where I can start with this low-level assembly stuff? Most compilers can output disassembly. Or output assembly. Yeah, CrackMe's is good for that stuff. I really like using the dump assembly features of whatever compiler you're using, because you can sit there and like make a function and then look at the disassembly of that function and kind of look at those bits in isolation. I find that really nice. I don't really know of places to get started, but Dan Collins just says step in debugger and switch to assembly view. Yeah, that's also very helpful, because you can, especially when you can see side by side kind of how the code maps together. I remember a long time ago reading the Art of Assembly book, which I think is still online somewhere, but I'm not sure if that's a good recommendation nowadays. Dark saying it used to hack on games, especially Morrowind. That's cool. I think like all of the low-level hacking I've done, minus some emulator stuff and some stuff for like Switch, has been making stuff for the demo scene. And that's why I have more experience with like debugging this stuff rather than reverse engineering it per se. Like Jeff says, for Rust, you can play around with it on Rust Playpen. Yes, which is awesome. Highly recommend that. The play.rust.com will just be able to do that for you. And it's very convenient. But I mean, I'd also try to find like some x86 or x64, like a specific architecture, like some kind of documentation. I mean, even if you just Google like x86 registers or x86 architecture, you'll find a lot of information that can at least help you read. Like x86 assembler can help you read the code that's actually there. So you'd want to couple like some disassembly and some CrackMe stuff with that kind of documentation as well. So when you see like RAX, you know what that is. Definitely going to help. But the nice part is that it's usually not that tough down there. Like you have to learn what a lot of the instructions stand for, but a lot of that ends up being shared between architectures. A lot of a lot of patterns. Just a specific kind of skill, but the rules are typically simpler down there. So you see, it says using the assembly output of C compiler is a good idea, as pointed. But if something is coded directly in ASM, it will look different than machine generated. Yes, that's definitely true. Dana Collins says, "What is the name of the CPU bug again? I need to order it, and I will do it now." That's computer architecture A quantitative approach. This is the 5th edition. I don't know if that's relevant. It's just the one I ended up with. Not my closest book right now. My closest book is actually physically based rendering. Gotta read up some more on that. Light coffee table reading. Dark Second, x86 is mostly move, right? Move and LEA tricks. Yeah, the physically based rendering book seems good. I haven't read that much of it myself yet. I need to, though. Bit heavy, but good. Yeah, that's what I expect. That's what I expect. I've been revisiting a lot of like calculus lately. Seriously says, I saw a compiler that only does move instructions. Yeah, move is Turing complete on x86. I think it is. I can't remember if you can move into the PC. But I think you can. I don't remember. That stuff is generally not helpful when trying to learn this stuff, by the way. But it's really cool things to really cool ideas to play with. Moveficator, yeah, that's what it's called. By the way, I just while we're talking about this, I just double clicked on this address just to see if we're skipping over something again. And it looks like we are. So it'll reads this global, looks at this bit, and then just jumps straight to over all of this. And then we'll preserve R31 and R3 coming out of that. And that's actually fairly interesting because then it means we can look at this as well and see the bit that's there. So that could be interesting. And see if that's some kind of conditional. Because I'm seeing a lot of code in here. And already there's stuff that touches R12 and R13. And this is the stuff that's causing us problems. So this is supposed to be behind some global variable. And we can kind of watch that. Then maybe we can see if we can find some interesting stuff there. CUC says the paper is called Move is Turing Complete. That's relevant. So it's 10 o'clock, and I'm getting pretty hungry. So I might head out, but I'm just leaving myself some notes here so that we can pick up, pick up here next time, or I may dig into this further in the coming week, but we'll see because I have a couple other things I'm working on. But at least we have a couple places where we can keep looking. There's definitely more digging to do here, especially like I want to see what this does, where this is written. What's being written to it. I also want to see if we can find the place again that writes this to 1. So I'm going to add a couple notes there. Actually, while I'm here, I've got the debugger open. I'm gonna do a couple things here. I want to spit out the registers because R4 is going to tell us where our globals are. This makes sense. This is right at the end of workram. So I want to see what this here is. 23928, and that'll be negative. And we can go to hex and we can add R4 0500, right? 8000, and we'll get this value in hex. Because it's quite likely that the case is that this interrupt is actually okay if it fires, but then there's some other state that's not being set up correctly that causes some of this code to run that causes problems. That's my current guess, and we'll just have to do more digging for that. But that's okay because we've already gotten a lot of additional information now than we had before we started, so that should be quite helpful. Oh yeah, Daniel Collins says there's a new edition of that book coming next year. Wonder what's new with that version. I'd be willing to bet it goes into more detail about GPUs, I mean, in particular mobile GPUs, because I know that that's kind of where the last one came out in 2012, and that's where a lot of that started to really change. Things like GPU on mobile started really becoming a thing then, so it would make sense. COC says maybe they added something about quantic architectures. Yeah, not sure. But definitely some more modern GPU information would be a really good addition to that book at this point. Steon Goot 1, thanks for the follow. But yeah, I think I'm going to call it quits for now, and then we'll probably end up taking a look at this next week. But at least we'll have a couple things to look into next time, so that should be helpful. But anyways, for now, I will see you guys later. Thanks for hanging out, by the way.